Welcome to Complex Analysis. Today, we are going to explore one of the most beautiful and powerful results in all of mathematics, the Cauchy integral formula. Imagine being able to know everything happening inside a room just by walking around its outside walls. That is exactly what this formula allows us to do with complex functions. It is a magical shortcut that will completely change how you evaluate complex line integrals. Let us dive in and see how it works. Now that we know what we are aiming for, let us understand the core idea. Imagine a magical security fence built around a city. If sensors on this outer fence record the temperature, a computer could perfectly calculate the temperature at any specific house inside without ever going in. In complex analysis, if we have an analytic function, which means it is smooth and has a valid derivative, and a simple closed contour, which is just a loop that does not cross itself, the exact same magic happens. The values of the function along the outer boundary completely dictate its value at every single point trapped inside. This incredible concept translates into a very elegant mathematical equation. Let us look at the Cauchy integral formula. Conceptually, it connects a single interior point to a line integral taken around the entire surrounding border. On the left, f of z0 represents the exact value of our smooth function at the specific interior point. On the right, we have a line integral around the closed boundary loop C. Inside the integral, f of z represents the function values sitting on the boundary itself. The denominator, z minus z0, measures the distance and direction from the boundary to our target interior point. Finally, the constant factor outside, 1 divided by 2 pi I, acts as a geometric scaling factor that perfectly balances the circular nature of the complex plane. Notice that as the point moves closer to the boundary, the denominator shrinks, meaning nearby boundary points have the strongest influence. Before we move on to using this formula, let us see this with a concrete visual. Here we are looking at the complex plane, with the real axis horizontal and the imaginary axis vertical. The large closed curve you see is our simple closed contour, labeled C. Notice the arrow on the curve indicating a counterclockwise direction, which is the positive sense for our line integral. Trapped safely inside this boundary is our specific point of interest, z0. The vector pointing from z0 to a point z on the boundary represents the distance z minus z0 that we just saw in the denominator of our formula. This diagram perfectly captures how the outer loop encloses and controls the inner point. Now that we have a clear picture of the formula, let us put it to work with a straightforward problem. We are asked to evaluate the complex integral of the exponential function e to the power of z divided by z minus 2. Our boundary path C is a circle centered at the origin with a radius of 3. Our first step is to identify the pieces of our puzzle to see if they fit the Cauchy integral formula. Comparing our problem to the standard structure, the numerator represents our smooth function. So we set f of z equal to e to the power of z. The denominator is z minus 2, which tells us our point of interest, z0, is exactly 2. Having identified our components, we must verify the most critical condition. Is our point actually trapped inside the boundary loop? Our boundary is a circle of radius 3, meaning it contains all points whose distance from the origin is less than 3. Our point is at 2. Since the distance from the origin to 2 is strictly less than 3, the point is safely inside the loop. Because the exponential function is smooth and analytic everywhere, all conditions are perfectly met. We can now rearrange the Cauchy integral formula by multiplying both sides by 2 pi I, allowing us to solve for the integral directly. With our rearranged formula ready, we simply substitute our specific values to find the solution. We replace z0 with 2 and we evaluate our numerator function at that exact point. We calculate f of 2 by plugging 2 into the exponential function, which gives us e squared. Finally, we multiply this by the 2 pi I scaling factor to get our final answer. The result is 2 pi I times e squared. Physically, if this integral represented the circulation of a fluid around the circular path, this result tells us the exact total accumulation, determined entirely by the field's behavior at the single point z equals 2. That first example was perfectly set up for us. Now, let us tackle a slightly harder problem where the denominator has more than one root, representing multiple points of failure or singularities. We want to evaluate the integral of cosine of z divided by z squared minus pi times z. Our boundary path this time is a circle centered at z equals 1 with a radius of 2. Our first step is to factor the denominator to find the specific points where the bottom becomes 0. Factoring out z gives us z multiplied by z minus pi. This reveals two critical points that could cause trouble, z equals 0 and z equals pi. Now we must act like a security guard and check which of these 2 points actually live inside our boundary circle. The circle contains all points whose distance to 1 is less than 2. For our first point, z equals 0, the distance to 1 is exactly 1, which is less than 2, so 0 is safely inside. For our second point, z equals pi, which is approximately 3.14, the distance to 1 is 2.14. Since this is greater than the radius 2, the point pi is outside the circle. The Cauchy integral formula only cares about points inside the loop, so we must handle the outside point differently. Since the point pi is outside our boundary, we group that part of the fraction into our smooth numerator function. By defining f of z as cosine of z divided by z minus pi, we have created a function that is perfectly smooth and analytic everywhere inside our circle. The only place it breaks down is at pi, which is safely outside our boundary. Our integral now perfectly matches the Cauchy integral formula structure, with our interior point z0 being 0. We have successfully isolated the single problem point inside the boundary. To find the final answer, we just need to evaluate our newly defined function at the interior point 0. We plug 0 into the numerator, giving cosine of 0, and into the denominator, giving 0 minus pi. Since the cosine of 0 is exactly 1, the value simplifies to negative 1 divided by pi. We now take this value and multiply it by our standard 2 pi I scaling factor. The pi in the numerator and denominator cancel each other out perfectly, leaving us with a very clean, simple imaginary number, negative 2i. This proves a crucial strategy. Always isolate the singularity inside the boundary and push everything else into the numerator. Now that we have successfully used this formula, let us understand where it comes from by deriving it step by step. We start by looking at the integral of our fraction around the large loop C. Because the denominator becomes 0 at the interior point, it is not analytic there. However, the principle of deformation of contours allows us to shrink our large, irregular loop down into a tiny, perfect circle, centered exactly at z0, without changing the overall value of the integral. Let us call this tiny circle C sub r, with an extremely small radius r. Because it is a perfect circle, we can describe any point on it using polar coordinates, setting z equal to the center point plus the radius multiplied by a rotating exponential angle term. Continuing our derivation, we need to replace the tiny step dz in our integral. We take the derivative of our polar expression with respect to the angle theta, which brings down an imaginary unit I. Now, we substitute these expressions for z and dz back into our integral over the tiny circle. Notice that in the denominator, the expression z minus z0 simply becomes the radius times the exponential term. This is a beautiful moment in the derivation because the complex terms in the numerator and denominator are about to cancel each other out perfectly. We cross out the radius and the exponential term from both top and bottom, leaving only the imaginary unit I and the function evaluated at points on the tiny circle. With our integral massively simplified, we imagine shrinking our tiny circle so much that its radius approaches exactly 0. Because our function is smooth and continuous, as the radius shrinks to 0, the points on the circle become the center point itself. Therefore, the expression inside the function simply becomes f of z0. Since f of z0 is just a constant number at that specific point, we can pull it completely outside the integral. The remaining integral is just the differential d theta evaluated from 0 to 2 pi. This step shows the incredible power of continuity in complex analysis, allowing us to collapse a path integral into a single point evaluation. We are now at the final stage of our derivation. By evaluating the simple angle integral from 0 to 2 pi, we get exactly 2 pi. Multiplying this by the constants we pulled out gives us 2 pi I times f of z0. To get the standard form of the Cauchy integral formula, we simply divide both sides of this result by 2 pi I. This isolates f of z0 on one side, proving that the value at the center is entirely dictated by the integral around the boundary. We have successfully derived the formula, showing exactly why this magical relationship holds true for analytic functions. So, we have proven that this formula holds. But why does it matter outside of pure mathematics? The Cauchy integral formula is the beating heart of complex analysis and has profound real-world applications. Engineers use this exact principle in fluid dynamics to model how air flows over an airplane wing. By knowing the air pressure and velocity along the outer boundary of the airflow, they can determine the pressure at any specific point near the wing. It is also heavily used in electrical engineering and control systems to evaluate incredibly difficult integrals that describe signal behavior. Without this formula, calculating the stability of a robotic arm or an electrical grid would require impossible amounts of brute force computation. We have covered a lot of ground today, so let us reinforce the most important ideas. First, the Cauchy integral formula provides a magical shortcut for evaluating complex line integrals without tedious manual integration. Second, it proves that for a smooth, well-behaved function, its value at any interior point is completely determined by its values on the surrounding closed loop. Finally, this principle reveals the incredible rigidity and interconnectedness of complex functions, where the boundary holds all the secrets of the interior. You have now mastered one of the most essential tools in complex analysis. Great job!